In the previous video, we used Burnside's lemma to tackle the cube painting problem, and in this video, we are going to use the lemma to tackle the non-mathematical applications, i.e. the chemistry and music problems briefly mentioned in the previous video. Burnside's lemma gives us this formula, and to use this properly, we simply need to have appropriate choices of the group G and the set X. Let's look at the chemistry application first. In this video, we will be considering a molecule called naphthalene, which has this chemical structure. More precisely, we are considering naphthalene with 4 chlorine substituents, or tetrachloronaphthalene. If you don't know organic chemistry, here is a brief explanation of what this diagram actually means. All the vertices here represent a carbon atom, and under stable circumstances, each carbon atom is like this one in the middle, having 4 bonds with something else. However, if we consider this carbon atom instead, it looks like it only has 3 bonds. So where does the hidden bond go? In a simplified chemical formula, any implicit bonds must be with hydrogen. We can also stick a chlorine atom here to substitute the hydrogen atom, which is why chlorine is usually called a substituent. So the question we are interested in is how many naphthalene molecules there are with 4 chlorine substituents. There are altogether 8 places for the chlorine substituents, and we choose 4 of them. You are right to think that the 3D structure might affect how we consider symmetries, but don't worry, because luckily all the atoms are on the same plane for this molecule. With this in mind, there are 4 symmetries that we need to consider, including the identity, a reflection along the vertical axis, a reflection along the horizontal axis, and a combination of the two, which is a rotation by 180 degrees. We now use Burnside's lemma to actually compute the number of naphthalene with 4 chlorine substituents. The first thing we need is the size of the group. Well, we have already listed all of them at the bottom, so we can substitute size of G as 4 at the top here. The next thing is the size of the fixes. Firstly, we will consider the fix of the identity. By definition, it fixes everything, so its fixed size would be the whole set. There are altogether 8 places that we can place our chlorine substituents, and we choose 4 out of it, so its fixed size is 8 choose 4. The next symmetry is the horizontal reflection. In this symmetry, 1 is swapped with 4, so in order for a molecule to be fixed by the reflection, both 1 and 4 need to attach to the same thing, i.e. both must have the chlorine, or both not having the chlorine and default to hydrogen. Similarly, we have other pairs of carbons swapping with each other under the reflection, and again, in each pair, both carbons have to attach to hydrogen together or chlorine together. So out of the 4 pairs of places for the chlorine substituents, we choose 2 pairs, making the fixed size 4 choose 2. Next up, we consider the vertical reflection. But similar to what we saw before, pairs of carbon are swapped under the reflection. So the argument for the fixed size being 4 choose 2 still applies. Now what about the 180-degree rotation? It might be a bit more difficult to see, but again, pairs of carbon atoms swap under the rotation, so this 4 choose 2 argument still stands in this case. So finally, to add up all the fixed sizes, we first add the 8 choose 4 for the identity, then add 3 times 4 choose 2, because for all the 3 other symmetries, their fixed sizes are 4 choose 2, which totals to 88. By Burnside's lemma, the number of orbits will be 22 after dividing by 4, the size of the group. So there are altogether 22 tetrachloronaphthalene molecules. Another application of Burnside's lemma is in music theory, which starts off with this circle. In Western music, there are 12 tones, and the pitch goes up when we go clockwise around the circle. So if you start with middle C, for example, going around the ring clockwise, you will end up at another C an octave higher. In this case, we are only concerned with the tones, not specific octaves, so there are 12 tones and that's it. In this video, we want to know how many trichords there are, or in other words, we choose 3 tones out of the 12, but there's a catch. If we can shift a chord to another chord, just by shifting each note an equal amount, we would count the 2 chords the same. So in counting how many trichords, we need to take rotation into account, because if we can rotate one chord to another, we count them the same. Similar to what we did before, we would need Burnside's lemma, and the first thing we need to do is to list all the symmetries we will consider, and compute the fixed size for each of the symmetries. We first consider the identity, which always fixes everything in the set. In this case, out of the 12 tones available, we choose 3 of them to form the trichord, so there are altogether 12 choose 3 things in the set, which is 220, which we record as the fixed size. What about the fixed size of the 30-degree rotation, clockwise or counterclockwise? C is transformed to C sharp, so if C is chosen, C sharp must also be chosen. But C sharp goes to D, so then D must also be chosen, and so on and so forth. So either every tone is chosen, or nothing is chosen. Since we are aiming for trichords only, the fixed size is 0 because no trichords gets fixed in this symmetry. For 60-degree rotations, C will go to D, so if C is chosen, D must be chosen as well, and so are E, F sharp, G sharp, and A sharp. But we only need to choose 3 of them, so we cannot choose the C note. If C sharp is chosen, D sharp must also be chosen, and in a similar way, the other 6 notes have to be chosen as well. So actually again, the 60-degree rotation does not fix any trichords. 90-degree rotations? Well, if C is chosen, then all these 4 have to be chosen as well. But the same thing happens if we choose any other note as part of the trichord, so the fixed size of the 90-degree rotation is still 0. But things start to change when it comes to a 120-degree rotation, because if C is chosen, only 3 notes need to be chosen because of it. There are altogether 4 trichords fixed by the 120-degree rotation, so the fixed size is 4. However, since both clockwise and anti-clockwise 120-degree rotations would have the same fixed size, we multiply this by 2. Next up, we have the 150-degree rotation. If C is chosen, then it turns out that through this logic, we would require every single tone to be chosen. So similar to what we did with the 30-degree rotation, the fixed size is 0 as well. The final symmetry is the 180-degree rotation. In this case, pairs of notes are swapped, so pairs of notes get chosen or not. But since we are considering 3-note chords and 3 is odd, the fixed size is 0 again. So we can finally use Burnside's lemma to tackle this problem. There are altogether 12 rotations that we have considered, and the total fixed size is simply adding everything in this column, which is 228. So there are altogether 19 unique trichords. While both non-mathematical applications do prove the use of Burnside's lemma, they are often cited as examples of an even more general result known as Polier enumeration theorem. But since it is a general result, it is bound to be notationally heavy. So I would direct those who are interested in finding more to the description, where you will find resources to learn about this theorem. Before you click away, here is something that I haven't talked about in my videos for a while now, which is the Google form linked in every video's description. It allows me to know your math levels and make the planning of future videos better. So please do fill in the form to help me create better videos. In any case, like, subscribe, hit the bell, and leave a comment if you enjoyed this video. See you next time. Bye.